Welcome back. Today on the Deep Dive, we're doing what we do best, plunging deep into a cutting-edge technical challenge in machine learning, specifically around large language models.
That's right.
And we're focusing purely on the mechanics today, the optimization, the technical implications. We'll be steering clear of non-technical aspects like ethics or inclusivity. That's just the lens for this particular exploration.
Be purely technical focus.
Exactly.
Yeah.
So the challenge is alignment. Getting these incredibly powerful language models, not just to be brilliant text generators, but to behave in ways that are genuinely helpful and harmless.
Easier said than done.
Right. It sounds simple, but technically specifying exactly what helpful and harmless means for every single possible scenario, well, it's basically impossible. So the field has largely landed on this technique called reinforcement learning from human feedback, RLHF.
A very widely adopted approach now.
It really is. And the core idea of RLHF is fascinatingly indirect. Instead of writing down explicit rules for good behavior, we collect human preferences on different model outputs. Which output is better.
Simple pairwise comparisons, often.
Yeah. And this data is then used to train a separate model, a reward model, which learns to predict how a human would score or rank a given output. This reward model becomes our technical proxy, right, for that ideal kind of unattainable ground truth reward that perfectly captures what we want.
It's the stand-in. We can't access the real thing, so we build this approximation.
Okay, now if you're thinking about this from an engineering perspective, the natural assumption is pretty straightforward. The better this proxy reward model is at mimicking human preferences. I mean, the higher its technical accuracy in ranking outputs the same way humans do. Well, the better the final language model will be after training.
It seems logical. A better map should lead to a better destination.
Exactly. It feels like a fundamental technical requirement. But here's where it gets really interesting and honestly a bit counterintuitive. Empirical evidence from various labs actually has shown that sometimes more accurate reward models don't actually lead to better language models when you train with them using RLHF.
Yeah, that's the puzzle.
Right. There's this technical accuracy paradox right at the heart of this widely used method.
And that technical paradox is precisely what the source material for our deep dive today gets into. We're pulling insights from excerpts of a research paper called "What Makes a Reward Model a Good Teacher?" An optimization perspective.
Great title.
It is. And this paper digs deep into the mechanisms of why RLHF training behaves the way it does. It looks at the reward model's role not just as a static judge, but as an active shaper of the whole optimization process.
Okay, so what's the big reveal? What's the core finding?
Well, the paper's core finding is quite technical, and honestly, it provides a pretty significant aha moment if you're working in this space. While accuracy is definitely important, for long-term alignment, preventing model misbehavior, that kind of thing.
Right, you don't want it going completely off the rails.
Exactly. But the paper demonstrates there's some pretty rigorous theoretical proofs and supporting experiments that a different technical property, reward variance, is fundamentally critical, specifically for efficient optimization during the RLHF policy gradient training phase.
Reward variance. Okay, so not just accuracy.
Not just accuracy influencing speed, no. It seems it's less about just getting the ranking right absolutely everywhere and more about how the reward signal technically impacts the learning landscape, the sort of terrain the language model is trying to navigate during training.
So our mission in this deep dive is to technically unpack why this reward variance property is so crucial. How does it directly affect the optimization process, the policy gradient part? And what does this shift in perspective mean for how we should technically evaluate and maybe even design these critical reward models going forward?
Precisely. We're diving into the core technical mechanism that makes a reward model an effective teacher for an LLM rather than just, say, an accurate score.
Okay, let's focus entirely on these technical details and their implications then. Let's unpack this. Maybe we should start by quickly grounding ourselves in the standard technical RLHF pipeline like the paper describes in section 2.1.
Good idea. It's a common structure, so it's good to have it clear. It usually kicks off with a phase called supervised fine-tuning, or SFT.
SFT, right?
That's right. So the SFT phase takes a base language model, often one that's already been pre-trained on just massive amounts of text, and then fine-tunes it on a data set of desirable inputs and outputs.
Like question-answer pairs or instruction-following examples?
Exactly. Think of it as teaching the model the basics of how to follow instructions or produce text in a specific desired format. This process results in an initial policy, which the paper calls pref. This is our starting point for the reinforcement learning bit. It already has the core language capabilities.
Got it. So we have a
Okay.
base model. It can generate text pretty well. It understands instructions thanks to SFT. Then comes the reward model step. Why exactly do we need this intermediate reward model, the RRM? You
Yeah.
touched on it. But why can't we just directly optimize for goodness?
Yeah, it goes back to that fundamental challenge you mentioned earlier. We just don't have a direct computable function that tells us the ground truth reward, RG, for any arbitrary piece of text the model might spit out.
The perfect measure.
The perfect measure, right? We assume this RG exists. It perfectly captures helpfulness, harmlessness, honesty, whatever traits we want, but we can't actually code it up directly. So as a proxy, we train the reward model, RRM, to try and approximate RG based on collected human preferences.
Okay. And how is this RRM typically trained? What's the actual technical process there?
The standard approach, as the paper describes it, involves collecting pairs or rankings of model outputs for various prompts. Humans, or sometimes even other AI models simulating humans, look at maybe two outputs for the same prompt and say, okay, output A is better than output B.
Simple preference labels.
Simple preference
Yeah.
labels, yeah.
Yeah.
The reward model is then trained using this preference data. A common technical method is using something called a Bradley-Terry log likelihood loss.
Right.
Intuitively, what this loss function does is encourage the reward model to assign a higher numerical score to the output that was preferred in a pair and a lower score to the one that wasn't preferred.
So it learns the relative ranking.
Exactly. By training on lots and lots of these pairs, the reward model learns to produce scores that hopefully align with how humans would rank the outputs. The paper also mentions you might not always train your own RM. Sometimes you might just use a pre-trained, publicly available one if it fits your needs.
Right. Okay. So we've got our initial language model policy, PREF, from SFT. We have our proxy reward model, RRM, trained to predict human preferences. The second major stage is reward maximization, usually done using policy gradient methods. What's the technical goal here? What are we actually optimizing?
Okay, so the technical objective now is to iteratively update the language model's parameters to maximize the expected value of the reward assigned by our proxy reward model, RRM.
The one we just trained.
The one we just trained, yes. And specifically, the expected reward for outputs generated by the current policy perf over a specific data set of prompts, which the paper calls S policy gradient algorithms, things like PPO, RLOO, GRPO. Those are specific RL algorithms are used for this updating process. They estimate the gradient of the expected reward and nudge the policy parameters in that direction.
And the objective function they're maximizing, this RLHF. The paper points out, and you mentioned it briefly, it's not just the expected RM score. There's that crucial KO regularization term involved, right?
Yeah.
Scaled by some coefficient.
Absolutely critical, yes. The full technical objective being optimized is maximizing the expected RRM over prompts in S minus O times the KL divergence between the current policy parf and the initial policy parf. That's O times KL parf.
And KL divergence, that's basically a measure of how much the model's output distribution has changed from its starting point.
Precisely. It's a technical measure of the difference or distance between the probability distribution of outputs from the current policy perf and the distribution of outputs from the initial SFT policy perf.
So what's the technical reason for subtracting this KL term? Why not just go all in on maximizing the proxy reward?
Well, the KL term serves a couple of really important technical roles. Firstly, it acts as a constraint. It prevents the policy from moving too far too quickly away from its starting point perf.
Why is that bad?
Well, if the policy explores parts of the output space that are wildly different from what the original SFT model would produce, a few things could happen. The reward model's predictions might become unreliable because it wasn't really trained on such different outputs, or the model might just start generating nonsensical text, sacrificing its basic language skills. So keeping the policy somewhat close to pref helps ensure the reward model is evaluated on outputs that are kind of within its reliable domain.
Okay, makes sense. Reliability.
Reliability. And secondly, and this is just as important, it helps preserve the general language capabilities, things like fluency, coherence, maybe even factual knowledge that the model learned during its huge pre-training and the SFT phase. Without that KL constraint, if you optimize really aggressively just for a specific reward signal on maybe a limited set of prompts, you could potentially damage these broader capabilities. It's called catastrophic forgetting sometimes.
Ah, right. So you don't want it to become great at one specific thing, but suddenly terrible at everything else.
Exactly. So the technical strategy is Use the reward model to guide the policy towards outputs that score high, according to human preferences, that's the RMM part, but keep the policy grounded and generally capable by not letting it drift too far from its initial skills. That's the KL part.
And the underlying hope, the gamble really, is that maximizing this proxy RRM score will, in turn, also improve the actual unmeasurable ground truth reward, RG.
Precisely. That's the standard technical pipeline the paper is analyzing. Now, the paper's real focus is on the quality of that crucial reward model and how its technical properties impact this whole optimization process.
Right. And as we mentioned, it defines two key ways to look at RM quality in sections 2.2 and 2.3. Accuracy and this new player, reward variance.
Well, let's start with accuracy. It seems pretty straightforward, but the paper adds some important technical nuance. So accuracy, formally defined in the paper as definition 1, basically measures how often the reward model's pairwise rankings match the ground truth reward, RG. So if for a given prompt X and two outputs Y and Y, the ground truth reward says Y is better than Ya, RGX, YGXY, and the reward model also gives Y a higher score than Ya, RRMXY, then that's a correct pairwise ranking. Accuracy is just the fraction of pairs where the RM gets the ranking right compared to the ground truth.
Seems like a very sensible metric.
It does. As the paper notes, it's a natural technical yardstick. It directly quantifies how well our proxy, RRM, aligns with the actual goal, RG, at least in terms of preference order. If maximizing RRM is supposed to push the policy towards outputs humans would prefer according to RG, then accuracy seems like the obvious thing to measure.
You mentioned nuance. The paper highlights a crucial detail about how we should measure this accuracy, especially in the context of the actual RLHF training, something about on-policy versus off-policy.
Yes, this is a really critical technical point. The paper stresses that accuracy should ideally be measured on policy. What that means is evaluating the reward model's ranking performance specifically on outputs that are likely to be generated by the current policy being trained, and specifically for the prompts that are being used during the policy gradient training phase.
Okay, why does that distinction matter so much? Why is on-policy accuracy the key thing here, rather than just accuracy on some general benchmark data set?
Well, think about the optimization process itself. During RLHF training, the reward model provides the gradient signal, right? But that signal is only based on the outputs the language model is currently producing for the training prompts S.
Oh, okay. It only sees what the current model does.
Exactly. So if you evaluate your reward model on some static benchmark data set, maybe with outputs or prompts that are very different from what your specific model is currently generating and being trained on that accuracy score you get, the off-policy accuracy might not actually reflect how effective that RM is within the actual optimization loop for your model.
It's like judging a teacher based on how well they answer questions about a subject they aren't actually teaching to their current students.
That's a good analogy, yeah. The paper cites prior work that also makes this important technical distinction. An RM might look great on a general leaderboard, high off-policy accuracy, but if it's not good at distinguishing between the outputs that your specific language model is generating right now for your specific training prompts, meaning low on-policy accuracy, then that high leaderboard score could be technically misleading about its usefulness as a teacher in this context.
Okay, that makes a lot of sense. The context of the actual training matters.
It really does. And this brings us back to the core puzzle. Even when researchers started looking at on-policy accuracy, the evidence still suggested that higher accuracy, even on policy, doesn't always reliably lead to better final language models after RLHF. There's still something else going on.
Which leads us perfectly to the second technical property the paper highlights, reward variance. This one feels less immediately intuitive than accuracy.
Right. It's a bit more abstract at first glance. Reward variance, as defined in the paper, definition 2, is the statistical variance of the reward scores assigned by the reward model, RRM. Specifically, it's the variance across outputs Y that are probable under the current policy POO for a given prompt X. Formally, Variance RRMXY.
Okay. Variance of rewards for probable outputs. Can we break that down a bit more simply? What's the technical intuition?
Okay, think of it like this. For any given prompt, your language model, at its current state of training, might generate a whole range of different possible outputs. Some might be pretty good according to the RM, some okay, some maybe not great. Reward variance measures how much the reward model's scores spread out across this range of outputs that your model is likely to produce right now.
So it's about the spread of the scores.
Exactly. If the reward model gives very, very similar scores to all the outputs the policy is likely to generate, maybe they're all scored between zero point 0.7 and zero point 0.8, then the variance is low. There's not much technical differentiation in the scores it's giving. But if it gives wildly different scores, maybe one likely output gets a zero point 0.2, another likely one gets a zero point 0.9, another gets zero point 0.5, then the variance is high. The reward model is technically separating or differentiating the outputs much more distinctly with its scores. It's measuring the dispersion, the spread of reward values specifically for the outputs the policy is currently generating and exploring.
Got it. So it's not just the order, but the numerical gap between the scores for things the model might actually do.
Precisely. And the paper builds on some prior technical work which showed a connection between low reward variance and a problem called vanishing gradients in reinforcement learning. This connection is absolutely key to the paper's main theoretical argument.
Okay, so variance is about the technical spread or differentiation of scores for outputs the model is currently producing. Accuracy is about getting the technical ranking order right. They seem like distinct technical properties. Let's dive into section 3, where the paper lays out its core technical theory. This is where we understand why variance is supposedly so critical for the policy gradient optimization process itself.
Right. This is really the technical crux of the paper's argument. It provides a fundamental mathematical proof connecting low reward variance directly to slow optimization speed in RLHF. The core technical result, which is formalized in Theorem 1, and a more detailed version, Theorem 4, essentially shows that if the reward model induces low reward variance specifically for outputs that are probable under the initial policy, then the technical landscape of the RLHF objective function, RLHF, becomes flat.
A flat landscape.
Okay.
Now, in practical terms for optimization, what does that technically mean for how the language model learns if the landscape is flat?
Well, in gradient-based optimization methods, which includes the policy gradient algorithms like PPO or RLOO used in RLHF, the model's parameters are updated iteratively, and they're updated in the direction indicated by the gradient of the objective function. The update rule is technically proportional to this gradient. You can think of it as the change in 8 over time, ddt, being equal to the gradient of the objective function evaluated at the current parameters.
So the gradient tells you which way is uphill.
Exactly, and how steep the hill is. Now, if the objective function landscape is flat, it means the gradient, our LHF, is very, very small, almost zero.
Like trying to climb a hill that's barely sloped.
Precisely. Imagine you're trying to climb a mountain in a thick fog, but instead of a steep slope, you find yourself on a vast, nearly flat plateau. No matter which direction you step, the ground barely seems to rise or fall. The gradient, which tells you the direction and steepness of the slope, is tiny.
So the updates are tiny.
If the gradient is tiny, the parameter updates, dAdTT, will also be tiny. This means the language model's parameters change extremely slowly with each optimization step. Consequently, the model's behavior, its output distribution, and the expected reward it receives will improve at an agonizingly slow pace. The technical optimization process effectively gets stuck, or just makes minimal progress per update. It's incredibly inefficient.
Wow. So the paper is making a technical claim here that even if a reward model is perfectly accurate-like, it technically knows which output is best if its scores for the outputs a current policy is likely to generate are all clumped really close together numerically. The technical optimization signal is just too weak, and the model simply can't learn efficiently.
That's exactly the core counterintuitive technical finding. Accuracy is about getting the direction of improvement right. This output is technically better than that one. But variance is about the magnitude of the technical signal for the specific outputs the model is currently exploring and trying to differentiate between.
Oh, okay.
If the technical difference in the reward model score between a slightly better output and a slightly worse output, both of which are probable under the current policy, is minuscule, then the computed gradient based on those scores will also be minuscule. The policy just doesn't get a strong technical push, a strong signal to shift its probability mass towards the better output.
And the paper provides technical proof for this.
Yes, the proof sketch in Appendix C.4 gives some technical insight. It builds on prior work that showed low variance implies a vanishing gradient, but it extends it by showing that under low variance, not just the first derivative, the gradient, vanishes, but higher order derivatives of the objective function also tend to vanish.
What does that mean practically?
Technically, it means not only is the immediate slope flat, but the rate at which the slope changes as you move, the second derivative or curvature, is also close to zero, and so on. This technically kind of locks the parameters into slow movement. It prevents the gradient from increasing rapidly, even over several steps. It's more profound stuckness.
Can you give us a slightly more specific technical detail from the theorem itself about the link between variance and optimization speed?
Sure. Theorem 1, and the more detailed Theorem 4, provides a formal technical lower bound on the time it takes for the expected reward, either the proxy RRM or the ground truth RG, to increase by a certain amount. Let's call it SURIC. The theorem shows this time is technically inversely proportional to the initial average reward variance across the training prompts, raised to the power of 1/3. So it scales like average initial variance, next 13.
Inverse relationship.
Right. The A notation technically means scales at least as fast as. So what this formally means is that if the initial average variance is low, that term, variance to the power of -13, becomes very large, which implies the minimum time required to achieve even a small reward increase will be very, very long. The optimization is technically bottlenecked by that low initial variance.
And this theory applies to the kinds of models we actually use,
Yeah.
like LLMs.
The theoretical analysis in the paper is developed for general autoregressive policies, which is the technical description that covers standard LLMs, equation 2. Now, some of the specific results, particularly the more detailed proofs showing how different RMs can lead to vastly different speeds, are derived for what are called tabular policies, equation 3. That's a simplified, more technically tractable case like a lookup table.
Okay, so simplification.
It's a common technique in theoretical RL, but importantly, the paper notes that their empirical results, which do use larger autoregressive models, strongly support the idea that the core phenomenon, low variance causing slow optimization, holds for these more complex models too. The analysis itself uses a technique called gradient flow, equation 4, which analyzes the optimization dynamics assuming small learning rates, which is generally how RLHF is done in practice anyway to keep things stable.
Okay, so the technical theory seems pretty rigorous. It points to variance being this fundamental technical bottleneck, controlling how quickly the policy gradient can actually climb the reward landscape towards higher scores. This leads us straight into section 3, discussing the really striking technical implications of this finding.
Exactly. And the first major implication directly confronts that initial paradox we talked about. More accurate reward models are not necessarily better teachers from a purely technical optimization standpoint, section 3.3.
This really does challenge our gut technical assumptions, doesn't it?
It absolutely does. The paper's theory technically explains this by showing that reward variance is fundamentally a distinct property from accuracy. Accuracy is about getting the technical ranking right. Is I better than you? Variance is about the technical separation or the spread of the scores for the outputs the model is likely to generate right now.
They can vary independently.
They can. And the paper formalizes this technical separation in Theorem 2 and the more detailed Theorem 5. It proves, mathematically, that there exist technical scenarios where a reward model can be perfectly accurate, like accuracy equal 1. It always ranks outputs correctly according to the ground truth RG, but still lead to an arbitrarily slower increase in the actual ground truth reward during RLHF training, compared to a reward model that is significantly inaccurate.
Wait, that sounds completely backwards. A reward model that technically makes mistakes in ranking can be a better teacher than one that is always technically correct. How is that even possible from a technical optimization perspective?
It's possible because, in that specific technical scenario constructed in the theorem, the perfectly accurate reward model might assign scores that are extremely close together, like numerically almost identical, for all the outputs that the current policy is likely to produce. It gets a technical ranking right, yes, but the numerical difference in the reward score between, say, the third best output and the fourth best output, assuming both are outputs the current policy might generate, could be absolutely minuscule.
Okay, so the relative order is correct, but the gaps are tiny.
Exactly. This results in very low reward variance for the on-policy distribution of outputs. And as we just discussed, low variance technically leads to a flat objective landscape and a tiny gradient signal. The technical parameter updates are minimal, the policy barely changes, learning crawls.
And the inaccurate one.
On the other hand, the significantly inaccurate reward model in this scenario might, just by chance, happen to assign scores that are much more spread out for the outputs the policy is currently producing, even if the ranking of those scores is technically wrong sometimes. This higher variance, this greater spread, typically provides a stronger gradient signal. It gives the optimizer a clearer direction, even if it's occasionally pointing slightly away from the absolute perfect ranking. This stronger signal allows the policy parameters to update faster and thus achieve a faster increase in reward, at least initially.
So the technical mechanism is that the inaccuracy doesn't completely break the optimization if the variance is high enough to provide a strong technical signal to learn something. Whereas perfect accuracy is technically useless for driving learning if the signal is too weak because of low variance.
That's the technical core of it, yes. Now, the paper is careful not to claim accuracy is irrelevant. It acknowledges accuracy is crucial for preventing reward hacking, where the policy learns to technically exploit flaws or loopholes in the proxy RRM to get high RRM scores, but actually low-ground truth reward. This is especially true if you train for many, many epochs.
Right. The longer you train, the more chances it has to find exploits.
Exactly. But the key technical finding is that in the typical, often relatively short training regimes used in practice for RLHF, a less accurate but higher variance model can technically be a more effective driver of ground truth reward increase simply because it provides a stronger, more usable gradient signal. Theorem 5 formalizes how this technical separation in optimization speed can occur, even providing examples with specific attainable accuracy values.
Okay, that's one major implication. Variance can technically trump accuracy for optimization speed, especially early on. What's the second big technical implication the paper highlights?
The second implication, which is covered in section 3.4, is that a reward model's technical effectiveness depends critically on the initial language model. It's guiding. It's not some universal technical property of the RM itself floating in isolation.
Meaning you can't just pick the single best reward model off a public leaderboard based on its accuracy score and expect it to be the optimal choice for technically training any language model you might have.
Not necessarily, according to the paper's technical findings and theory. The core technical reason comes back to variance again. The same reward model, RRM, can induce high reward variance when it's applied to the outputs that are probable under the policy distribution of one initial language model, say Llama 2, 7B, SFT.
Okay.
But it might induce low reward variance when applied to the outputs probable under the policy distribution of a different initial language model, say Pythia 6B, SFT.
Because the starting models produce different kinds of outputs.
Exactly. Remember, variance is a technical property measured with respect to the current policy's output distribution. If two different initial policies have different technical likelihoods of producing various outputs for the same set of training prompts, S, then the same reward model, RRM, might assign very different sets of technical scores to the probable outputs under each policy. The spread of these scores, the variance would therefore naturally differ depending on which initial policy you start with.
So the RM's effect isn't fixed. It depends on what it's scoring.
Precisely. And this technical observation leads directly to the result in Theorem 3 and Theorem 6, which formally states that for different initial language models, different reward models will technically prove to be better teachers, specifically in terms of driving reward increase during policy gradient training.
This seems to directly challenge the technical premise behind creating universal reward model benchmarks, right? Things like Reward Bench or the HELM rankings, which try to rank RMs based on accuracy on some fixed data set, kind of independent of the specific LLM that will eventually be used to train.
That's a key technical implication the paper draws, yes. It argues that these kinds of benchmarks, while useful for measuring general alignment with human preferences perhaps, might not be the most relevant technical evaluation if your primary goal is effective and efficient RLHF training.
Because they don't capture this policy-dependent variance.
Exactly. The paper technically argues that evaluating an RM's effectiveness for RLHF requires considering its dynamic technical interaction with the specific policy distribution it will be optimizing over. Its variance property, which is technically crucial for the speed of optimization, is inherently policy-dependent. You can't fully assess the teacher without knowing the student.
Okay, that's some fascinating technical theory. Really shifts the perspective, but does it hold up when you try it out in practice? Let's move on to section 4, experimental validation. Did the paper's experiments using actual language models technically corroborate these theoretical findings about variance and policy dependence?
Yes, they did. The paper includes a set of experiments in Section 4 using language models up to 8 billion parameters from families like Pythia and the newer Llama 3.2, and they use standard technical RLHF datasets like Alpaca Farm and ultrafeedback. And the experimental results they present technically support the theoretical conclusions quite strongly.
How do they technically set up these experiments, given that getting true, large-scale human preferences for evaluation is really hard? What did they use as their ground truth reward?
That's a great question. In their technical setup, described in Section 4.1.1 and Appendix E, they acknowledged that difficulty. So they simulated a high-quality ground truth reward. They used the ARMOR-M model, which is itself considered a very strong publicly available reward model, as a proxy for true human preferences.
Okay, so they used a good RM as the oracle.
Essentially, yes. They took the ultrafeedback dataset, partitioned it, used about 80% of the preference pairs to train various proxy reward models that they wanted to test, and kept the remaining 20% as the set of prompts, S, for the actual policy gradient training step. Crucially, for evaluating the final models, they used the ARMOR-M model to relabel the preference data associated with the prompts in S, creating a simulated ground truth reward signal for comparison.
Clever. And what about the models in training?
They use different language models as the initial policies, BRIF, including a Pythia 2.8b model and various Llama 3.2 models. For a fair technical comparison of variance effects, they made sure to normalize the different reward models they tested to the same score scale. They then used RLOO, which is a standard policy gradient algorithm often used in RLHF, to train the policies. Performance was evaluated by calculating the average proxy reward and the average simulated ground truth reward on the training prompts S, typically by sampling multiple outputs for each prompt during evaluation.
And crucially, how did they technically measure the variance and accuracy of the RMs in these experiments to directly test the theory? Was it on policy?
Yes, absolutely critical point. They calculated both accuracy and reward variance on policy. That means they specifically looked at outputs sampled from the initial policy on the training prompts to assess these properties for each RM. This allowed them to directly test the theoretical prediction that it's the on-policy variance that should correlate with the initial optimization speed. They also measured off-policy accuracy on the original ultra-feedback outputs, just for comparison.
Okay, setup sounds solid. Let's get to experiment 1. Accuracy versus variance in practice, section 4.1. What were the key technical results here?
The technical results, which you can see visually in Figure 2 and are summarized in Tables 1 and 2 in the paper, were quite clear and lined up really well with the theory. What they did was technically train several different proxy reward models. These were designed to have varying levels of on-policy accuracy, ranging all the way from 100% down to 0%, basically random.
Wow, even 0% accuracy.
Yeah, as a baseline. Plus, they included a really interesting special case. A reward model they specifically engineered to be perfectly accurate, 100% on-policy and off-policy accuracy, but simultaneously designed to induce low reward variance for the initial policy's likely outputs.
The theoretical bad teacher.
Exactly. The accurate but low variance case predicted by the theory. And what they technically observed was a strong positive correlation between the measured on-policy reward variance of these RMs and the rate at which both the proxy reward, RM, and more importantly, the simulated ground truth reward, RG, increased during the initial epochs of the policy gradient training.
So higher variance meant faster learning.
Yes. Table 2 gives the technical correlation coefficients. They found a Pearson correlation of 0.834 between the on-policy variance and the actual increase achieved in the simulated ground truth reward. That's a strong positive correlation.
And what about accuracy? Did higher on-policy accuracy correlate with faster learning?
No, quite the opposite in the results. On-policy accuracy actually showed a negative or, at best, low correlation with the rate of reward increase. For instance, its Pearson correlation with the simulated ground truth reward increase was meta 0.283, a slight negative correlation.
So empirically, higher technical on-policy variance meant faster technical learning progress, while higher technical on-policy accuracy actually seemed slightly detrimental to speed, or at least didn't help. That directly supports the technical theory, right?
It really does. And that special case, the perfectly accurate reward model that was designed to have low variance, it technically performed poorly, just as the theory predicted. In terms of the rate of reward maximization, it was consistently outperformed by less accurate proxy reward models that just happened to induce higher variance. You can see this clearly in Figure 2.
That's pretty compelling evidence.
It gets even more striking. The paper found that in some specific cases, training with one of their proxy reward models, remember, these are imperfect approximations, trained on only part of the data, actually led to better performance, a higher increase in the simulated ground truth reward, than training directly with the simulated ground truth reward model itself.
Get out! How is that possible?
It happens specifically when the proxy reward model induced significantly higher variance than the simulated ground truth model did for that particular initial policy's output distribution. You can see this in Figure 2 as well. The proxy, despite being wrong more often, generated a better technical gradient signal because its scores were more spread out for the outputs the policy was exploring.
So the proxy was a better teacher in that case, even though it wasn't the oracle.
From an optimization speed perspective, yes. Now, this technical finding mainly holds for the initial training epochs. The paper notes that if you trained for much longer, the inaccuracies in the proxy model could lead to reward hacking, and the ground truth model would likely win out eventually. But for typical, shorter RLHF runs, variance was dominant for speed.
Wow. Okay. And did the experiments also confirm the on-policy versus off-policy distinction?
Yes, they did. They found that reward models which had high off-policy accuracy looked good on the general benchmark, but had low on-policy accuracy were technically poor teachers in the actual training loop and were also more susceptible to reward hacking. This further reinforces the idea that it's the on-policy properties, particularly variance, that are most technically relevant for the optimization effectiveness. They also ran additional experiments, detailed in Appendix D.1 using different models, dataset sizes, and RL hyperparameters, and found similar trends, suggesting the results weren't just an artifact of one specific setup.
Okay, very strong support for the variance over accuracy for speed idea. What about the second technical implication, the idea that RM effectiveness depends on the specific LM being trained? Did Experiment 2 technically bear that out?
Yes, Experiment 2, described in Section 4.2, was designed specifically to test this policy dependence. They took different initial policies specifically, variants of Pythia and Llama 3.2 models, including versions that had just SFT and versions that had also gone through instruction fine-tuning, and they evaluated several publicly available reward models on each of these initial policies. These public RMs had varying published scores on benchmarks like Reward Bench.
So comparing off-the-shelf RMs on different starting LMs.
Exactly. And the technical results, which are presented in Figure 3 and detailed further in Table 9, confirm the theory quite nicely. The reward model that achieved the highest simulated ground truth reward increase after policy gradient training technically varied depending on which initial language model was being trained.
So there wasn't one single best reward model across all the different language models they tested.
Not in terms of driving reward increase effectively through policy gradient, no. For example, in their tests, a model called RM-Tulu V28B was the most effective technical teacher for the Llama 3.21b SFT model. But for a Pythia 1b SFT model, a different reward model, GRM Llama 3.23b, performed better.
Interesting.
The technical data in Table 9 in the appendix really shows this. It lists the measured reward increase achieved by each tested RMLM combination, alongside their corresponding measured on-policy variances and accuracies for that pairing. The empirical evidence clearly shows that the technical interaction between the RM and the initial policy's output distribution matters significantly. The same RM induced different technical variance levels when paired with different initial policies, and that variance level technically correlated strongly with the optimization speed observed for that specific combination.
So really it's about the pairing.
It seems so, based on these results. They also included more experiments in Appendix D-Way 2 using different model scales up to 3 billion parameters and also trying a different policy gradient algorithm, GRPO, instead of RLO. They reported that the results were consistent, which technically supports the generalizability of these findings across different tested policy gradient algorithms and model sizes, at least within the range they tested.
Okay, the empirical results seem to really back up the theory. This is a significant technical shift in how we should probably be evaluating reward models, isn't it? It's not just about getting a high static accuracy score on some benchmark anymore.
It really isn't, if this holds more broadly. It emphasizes the dynamic technical interaction with the policy's output distribution during the actual training process.
It forces us to think about the reward model not just as like a passive judge grading papers after the fact, but as an active technical component that's actually shaping the optimization landscape, the terrain that the language model has to learn on.
That's a great way to put it, yeah.
Okay, let's try to connect these dots now and maybe look ahead a bit. Section 5 in the paper touches on related technical work and hints at future directions. How does this paper technically fit into the broader landscape of RLHF research? What's novel here?
Well, the paper positions its work as being the first technical analysis to specifically characterize how properties of the reward model itself, particularly this variance aspect, technically affect the policy gradient optimization dynamics specifically within the RLHF framework.
Focusing on the optimization part.
Exactly. A lot of existing technical work on RLHF theory often focuses on other aspects, like proving theoretical guarantees for finding optimal policies under certain algorithm assumptions, or maybe bounding the sample complexity needed to estimate the reward model accurately. But this paper specifically zeroes in on how the RM's properties, relative to the current policy, influence the technical shape of the optimization problem that the policy gradient algorithm is trying to solve.
How does it relate to other work on why policy gradient can be hard?
It connects to the technical literature on optimization difficulties in policy gradient methods more generally, like the problem of vanishing gradients. Vanishing gradients were previously noted, for example, when policies become almost deterministic, they only produce one output. But this paper builds on more general technical work, showing that gradients technically vanish whenever reward variance is low, regardless of whether the policy is deterministic.
Ah, so low variance is a more general cause of vanishing gradients.
It seems to be a broader condition, yes. And it's particularly relevant for large language models because they rarely become truly near deterministic in their vast output space during typical RLHF training. So low variance could be a key reason for slow training, even when the model is still exploring.
Interesting. What about things like reward shaping or ensembling RMs? Does the paper touch on those?
It does briefly. Ensembling, combining multiple reward models has often been suggested as a technical technique, mainly to combat reward hacking. The idea is that averaging predictions from several RMs might smooth out the individual flaws or biases of any single model.
Makes sense. Safety in numbers.
Right. But this paper suggests another potential technical benefit of ensembling, viewed through this new optimization lens. It hints that combining multiple RMs might also reduce the chance of hitting a critically flat objective landscape caused by low variance. Section 5 mentions this.
How would that work?
Well, the technical hypothesis, though not proven in the paper, is that if you combine several different RMs, the chances that all of them simultaneously induce critically low variance for the current policy's output distribution might be lower than the chance for any single RM doing so. Maybe their low variance regions don't perfectly overlap.
That's a really interesting technical hypothesis. So ensembling might not just improve accuracy or robustness, but could actually speed up the optimization by ensuring a better gradient signal.
Potentially, yes, but the paper doesn't technically detail how ensembling specifically affects variance or prove this benefit. It just posits it as a plausible benefit suggested by their optimization perspective. That's definitely one of those areas ripe for further technical exploration based on these findings.
Yeah, like would simple averaging of scores technically increase or decrease the resulting variance for the on-policy outputs? Is there a clever technical way to train an ensemble specifically to maximize variance alongside accuracy? Lots of open technical questions there.
Absolutely.
Speaking of open questions, what technical limitations and future directions does the paper explicitly lay out in section 6.1? Where should research go next, according to them?
A major one they highlight is the technical challenge of figuring out how to actually train or modify reward models so that they inherently induce sufficient reward variance while also maintaining high accuracy. That's the golden ticket, right? Get both.
Right. High variance for speed, high accuracy for correctness.
Exactly. And they point out that the obvious first idea, just naively scaling up the raw reward scores to increase variance, variance scales quadratically with the scores, so scaling scores by c increases variance by c squared, didn't actually seem to help in their preliminary experiment.
Oh, why wouldn't simple technical scaling work? That seems like the most direct way to increase the spread.
It seems intuitive, but the paper suggests a potential reason. When the variance is already critically low, the underlying expected reward gradient signal is vanishingly small. Any gradient estimate you get from sampling outputs during training is likely to be dominated by noise relative to that tiny true signal.
Okay.
Now, if you just scale up the rewards, you technically scale up this noise right alongside the signal. If your signal-to-noise ratio was already parable because the true variance was low, simply scaling everything might just amplify the noise problem, making the gradient estimate even less reliable, rather than providing a clean, usable, stronger gradient signal.
Ah, I see. So it suggests the technical issue isn't just the absolute magnitude of the rewards, but the relative separation of scores assigned to different outputs that the policy is actually generating. The signal itself needs to be clearer relative to the noise.
That seems to be the implication. So potential technical approaches they mention include things like encouraging a larger margin between the reward scores assigned to preferred versus dispreferred outputs during the reward model training phase itself. They reference some prior technical work on margin-based loss functions that try to do this.
So explicitly push the scores for good and bad examples further apart.
Exactly. That would directly address the issue of scores being too clumped together. Another possibility they mention is maybe coupling reward scaling with improved technical gradient estimation techniques, ones that are specifically designed to be more robust to noise, especially in this low variance regime. But technically designing the specific loss functions or maybe even new RM model architectures or specific training strategies that explicitly optimize for this margin or variance property alongside accuracy, that's highlighted as a key technical challenge going forward.
Makes sense. What other future directions did they mention?
They also wonder if these technical insights about variance might apply even when training LLMs on tasks where you have automatically verifiable rewards. Think about coding or mathematics problems, where you often have a clear technical success or failure criterion that the code runs correctly or the math proof is valid.
Right. No human preference needed there. You have a ground truth.
Exactly. But the question is, could the way we design these verifiable technical rewards, or maybe the way we select the training data, they reference work on data selection for reward, influence the variance of this verifiable reward signal? Could we design them to ensure sufficient variance for efficient policy grading optimization on those tasks too? The concept of variance might still be technically relevant for optimization speed, even without a human-in-the-loop preference model.
That's a neat extension. Anything else?
And finally, they circle back to the point that the technical importance of different RM properties really changes depending on the specific alignment method being used. They give the example of best-of-n sampling, which we discussed briefly. In Section B, in Proposition 1, they actually prove that for best-of-n, a perfectly accurate reward model is always technically optimal.
Right, we touched on this. Why the technical difference again? Why is perfect accuracy the undisputed king for best of n, but not necessarily for RLHF policy gradient?
It boils down to how the reward model is used in the technical mechanism. Best of N doesn't use the reward model to compute gradients for policy updates. It just generates N candidate outputs from the current policy, uses the RM to score all N of them, and then simply picks the one with the highest score.
It's just a selection tool.
Exactly. If the RM is perfectly accurate, it will always technically identify and select the output that has the true highest ground truth reward among those N candidates. The optimization landscape, the magnitude of the gradient signal, the variance, none of that matters for the selection step itself. Only the technical ranking is used.
Whereas policy gradient needs that gradient signal magnitude.
Precisely. RLHF with policy gradient uses the RM's actual numerical scores to compute a gradient estimate that technically guides the policy's exploration and its parameter updates. In that process, the technical differences in scores between likely outputs and thus the variance become paramount because they determine the magnitude and reliability of that gradient signal.
Okay, that really clarifies the distinction.
Yeah, and it highlights that the fundamental technical mechanism of the alignment method you choose really determines which technical properties of your reward signal are most important for achieving the goal. So how do variance and accuracy technically play out in other popular methods, like, say, DPO, direct preference optimization, or maybe different forms of rejection sampling? That's another area the paper suggests is ripe for technical exploration, building on the foundation they've laid here about variance being critical for gradient-based methods.
This is genuinely technically fascinating. It really shifts the focus, doesn't it? From just, is my reward model accurately reflecting human preferences, to a much deeper technical understanding of how does the shape and the properties of my reward signal, particularly its variance relative to my current policy's output distribution, technically impact the reinforcement learning process itself.
Exactly. It compels us to analyze the reward model not just as a static predictor of preferences, fitting a data set, but as a dynamic technical component operating within a complex optimization loop. And it raises hard technical questions, like how can we even technically characterize or predict the variance a specific RM will induce for a specific LM's output distribution before we actually start the expensive RLHF training? That's a non-trivial technical problem in itself.
Yeah, predicting that interaction seems tough.
Very. So, to kind of wrap up this deep dive, focusing purely on the technical aspects as we set out to do, I think the key technical takeaway from this paper is pretty profound, really. For effective and efficient RLHF optimization using policy gradient methods, a reward model needs more than just high accuracy in ranking outputs. It critically needs to induce sufficient reward variance for outputs probable under the current policy. Why? To ensure the objective function landscape isn't
based on static accuracy benchmarks, or independently of the specific language model they'll be paired with for training, is likely fundamentally limited, at least if your goal is fast, effective RLHF training.
That's the strong suggestion, yes. It's really about that crucial, dynamic, technical interaction between the reward signals properties, both accuracy and variance, and the policy's learning process during optimization.
And the paper's theoretical proofs, backed up by their empirical evidence using actual language models, seem to clearly demonstrate that focusing on reward variance alongside accuracy is essential. Essential for technically understanding, evaluating, and ultimately designing better reward models if we want to achieve faster, more effective language model alignment through RLHF.
Couldn't have said it better myself.
But it definitely leaves us with some significant technical challenges ahead, doesn't it? Especially figuring out how to reliably train reward models that possess this desirable high variance property in conjunction with high accuracy. That seems like the next frontier.
Indeed. It pushes the technical boundaries of reward model design and evaluation. It requires us to think beyond just fitting human preferences and delve much deeper into understanding the underlying optimization mechanics involved.
So, thinking about those challenges, what specific technical puzzle stands out most to you after this deep dive? Based purely on these technical findings we've discussed, is it maybe designing those novel RM architectures or training objectives we talked about, the ones that explicitly try to manage variance alongside accuracy, perhaps incorporating new terms right into the loss function?
Oh.
Or maybe it's technically exploring how different policy gradient algorithms themselves, beyond just RLOO or GRPO, might be more or less susceptible to this landscape flatness issue caused by low variance. Just something purely technical for you, the listener, to consider as you process all this information.